Everybody, so this lecture for our fire ecology class, we're going to be focusing on fire weather principles and the different parts of the weather that really influences fire behavior. So let's just kind of start with the basics with regards to weather. So if we're going to define weather, we're going to define it as the current state of atmospheric conditions. And what's really important is for us in the idea of wildland fire ecology is thinking about weather in terms of the fire behavior triangle, and thinking about it in terms of being the most dynamic part of the fire behavior triangle. Because when we think about the things like topography will change, but topography doesn't change over time, really, right? If we have a mountain or a hill or it's flat, it's that way, for a long time. It might change eventually, but for the most part, that's really going to stay static over time. Whereas fuel can change over time, and it can be in different stages of fuel. But for the most part, we're going to know what we're dealing with, right? If it's a forest, even if the forest gets burned at some point in time, it will probably go back to a forest. So we got a good idea. Whereas the weather, it can change day to day. If you live in some places, like when I lived in the southeast, it was more like the weather could change hour per hour or minute by minute. And so it's definitely the most dynamic part of the fire behavior triangle. It definitely has a large influence on fire outcomes because of its effect on fuel moisture and on the efficiency of heat transfer. It can vary over short distances across a landscape, and the elements that we're going to focus on temperature, wind, and atmospheric stability. So when we're talking about weather, we're really talking about the state of the atmosphere that surrounds the Earth. And so when we say the current conditions of the atmosphere, we're talking about the fact that weather implies motion in the atmosphere, and that there's all these things actually happening in the atmosphere. The atmosphere is really dynamic. It's not static. And so weather is concerned with that changing nature, that dynamic nature of the atmosphere. So things like temperature, pressure, wind speed and direction, humidity, visibility, clouds, precipitation, all these things are parts of weather and things that can change quickly, and for fire behavior could lead to a change in fire behavior. And so the three that we're going to focus on temperature and moisture, and the relationship between them, and how there's an inverse relationship between temperature and relative humidity. We'll look a little bit at precipitation, and basically focus on kind of the idea that fire wants to eliminate moisture. In terms of atmospheric stability, we're talking about resistance to motion, and we'll go in depth on that. And you could have stable atmospheres, and you could have unstable atmosphere, and you can have areas where you have a mixture of both. One of the big things that could happen with stability is that it can lead to thunderstorms, which we know lightning is one of the major ignition causes of fires here in California. And then wind. Wind provides oxygen for the preheating of fuels. Wind can also drive and change fire behavior. So it's also going to be extremely important. And these are the ones we're going to focus on for the next part of the lecture. So let me move myself out of the way so you can see that. So let's start off with temperature. So temperature is going to vary by region and altitude. That shouldn't be really surprising to anyone. But in general, warmer temperatures are going to be found at lower elevations and latitudes. We're going to see definite local variation on the California coast. We're going to see lower temperatures due to the coastal marine layer and the cool marine air. And then higher elevations are usually cooler than low elevations due to the adiabatic lapse rate. And we're going to talk about that in just a bit. So how does temperature work at the most basic level of it? Okay, and during the day, solar radiation delivers more heat than is lost. So we know in understanding how the greenhouse effect works that we get solar radiation from the sun. It comes through the atmosphere. It reflects off of things. Some of it gets absorbed, some of it reflects off. So in terms of that absorption reflection, during the day, we have more heat being absorbed than being reflected. Whereas during the nighttime, when we don't have that solar radiation, we've got much more heat reflected and much more heat being lost as opposed to heat coming in. So the ground cools, everything gets cooler. Now, what can change this? So shade can change this. Things like trees, mountains, things that could change the amount of solar radiation that you could get depending on the angle of the sun. Clouds can also be both, I guess, somewhat problematic with temperature and somewhat helpful as well. So, I mean, if you want it to be hot and you got clouds, clouds are going to keep in some of the heat, but also prevent some heat from coming in. So, like during the day, if it's a cloudy day, it's not going to get as hot necessarily as you might want it to be, although it's going to keep more heat for longer. And at night, if you have a cloudy night, you're going to have a much warmer night than if it was clear skies. So it kind of just depends with clouds on what you're looking for. In the south, if it was cloudy, usually it meant it was going to be moist. There might be some rain, and it meant, going to be hot and wet and sticky. Not quite fun. When do we see net gains during the day? For most of the time, we see it during the summer. The peak is in July, like around 4th of July. On the coast, actually, we see it in August is when we have the biggest net gain. Our biggest net loss in terms of heat is for everywhere in California is around winter solstice. And so if we look at this chart here on the left, or this graphic, if you will, just kind of shows 2020 wildfire potential, and you can see how a lot of the areas out here in the west are set up for high wildfire potential because of higher temperatures and not a lot of available moisture, either precipitation or snow. So with trying to understand the dry adiabatic lapse rates, we have one key core tenet that we have to really understand, and that's the idea that air expands and cools when it's lifted, and air compresses and warms as it lowers. So if we take a look on the right here, and we see the ground here, we get our solar radiation from the sun. It's going to heat up these little air parcels and the moisture within these air parcels. So because it heats it up, it then rises off the ground, and this is through evaporation or transpiration, we start getting this moisture coming back up, and as it rises, it's going to cool. And as we go up, because we know it's colder up here and it's warmer down here because of that solar radiation's getting absorbed at the ground, whereas it's getting reflected above, we can get it to where the warm air rises, and then it can cool. And if there's enough moisture and enough pressure from up above, then we get cloud formation, and we get condensing to happen. And so that really depends on whether there's pressure or not, or how much. Well, there's always pressure, but how much pressure is above, and can it go through, or is it getting held back by the pressure? Depends on where you are. We'll talk about it some more as we go through the slides. In terms of the adiabatic lapse rate, and that just really has to deal with this same idea of vertical motion of air, the idea that an air parcel is going to expand and cool as it goes up in the air. And the reason why it compresses closer to the ground is just the idea of that heat keeping it together. Air wants to spread out, but because of pressure, because of the idea of the heat keeps it, the air compresses and warms with heat. It expands and cools when there isn't heat. And so that's why we're going to it's going to become really important just with the idea of pressure. So pressure, in terms of where do we have the most pressure? You have the most air pressure at sea level, or what we would kind of consider the ground. Or if we want to think about the valley versus the Sierra Nevada mountains, there's much more pressure in the Central Valley than there is up in the Sierra Nevada mountains, because as you go up, the air, you have cooler temperatures, so the moisture in the air particles can expand out, and because they can expand out, there's not as much of a feeling as pressure. Whereas towards the valley and towards the ground, towards sea level, any of those things where we're much lower, that means that all of that moisture wants to compress and warm. And if it wants to compress and warm, that's going to create pressure. Whereas if we go up in altitude to where it's colder and the air can then expand and spread out, we don't feel as much pressure. Aspect then becomes important in terms of solar radiation. So aspect is the direction the slope is facing. So if I have a southern aspect, it is a south-facing aspect. So if I was talking about Bakersfield College and where the bluffs are, the bluffs have a northern aspect. The bluffs are facing north. They're not, when we think about where they are on Bakersfield, with Bakersfield College, if we're looking down into the Kern River Valley down there, it's a northern aspect because that slope is facing north. Aspect is important in terms of fire behavior because it will affect the amount of solar radiation that's received and the amount of wind that's received. So in the northern hemisphere specifically, and I find this just really interesting, south and southwest aspects are most favorable for fire start and spread. Why? And the reason is, it's because they get more sun, they have lower humidity, and they have higher fuel temperatures. And if you're saying why, it's because solar radiation is greatest when the slope is perpendicular to the sun angle. So when does that happen here? That happens here in the afternoons. And so that means that what is going to get the most solar radiation? Well, because we're in the northern hemisphere, the sun appears in the east and then disappears in the west. And it does that on a southerly axis. So that means it's going to go from east to west and it's going to stay south of us, or at least south in terms of angle. And so what does that mean? It means that in the mornings, north and east are going to be the places that are warmest. But remember, during the day, it's not as hot on those north and east aspects. Whereas then the southern side of something is going to get a little bit of that morning sun. It's also then going to get the midday sun. It's also then going to get the afternoon sun. And then the afternoon sun is going to be that hottest when that solar radiation angle is at its greatest. So that means that southern and western slopes are going to get the sun when there's low humidity, when the sun angle is its greatest. So we're getting that greatest amount of radiation, which means you're going to get higher fuel temperatures and you're going to get drier fuels on southern and western slopes. Eastern aspects are going to dry out dry out faster earlier in the day, and westerly aspects are always going to be drier than eastern. So to just kind of paint that picture, so north versus south, the northern hemisphere versus the southern hemisphere. On north sides versus south sides, the sun, we're going to get that angle, so it's going to be warmer on southern aspects than it is on northern aspects. So we're going to expect, if we're going to get trees and shrubs, we're going to see them much more on northern aspects than we will on southern aspects. And in terms of east versus west, we're going to see colder morning temperatures when the sun shines in the east, and then we're going to get warm air temperatures when the sun's shining in the west. And so if we look, here's just a comparison of a north-facing slope and a south-facing slope. And that south-facing slope, we can see sees much hotter temperatures during the day. Now, of course, it kind of depends on all sorts of things in terms of solar radiation. What are we talking about in terms of topography? You know, does that mean we get no sun on the northern side? No, because the angle of the sun that's coming from up above, it just means that you're going to get much more on the south side than you are on the north side. And so here's a really good example to me of that. And so this image on the left shows the variation in temperature and relative humidity with aspect. So you can see low temperature, high relative humidity versus high temperature, low relative humidity. So on the southern ridge, you can see that you get really high temperatures, really low RH down here towards the toe of this southern aspect. Whereas the northern one, you're not getting anywhere near as high of temperatures, and you're definitely getting some low temperatures, some areas where you're not getting very much sun at all. On the right here, you can see field temperatures and field flammability by time and aspect. So you can see that because the eastern aspects get sun in the morning, you're going to get the big bump in field temperature earlier in the day. But then as the sun moves away from the east towards the west, it dips off. The north will get it a little bit later because towards midday the sun is at its highest angle, so the northern sides are getting hit a little bit more, and then it'll dip off, whereas the south is definitely going to get much higher temperatures, as are the west, and they're going to get it peak towards that midday and then really die off, whereas the west is going to start getting it and get it much later than everybody else. So in terms of fuels, if you really want to see a really great example of this, drive up and down. Let me get myself out of these sun rays. There we go. Drive up and down the Grapevine, because it's really obvious on northern and southern aspects. You can really see the difference between lighter fuels where it's sunnier and drier, so more grass, more chaparral, shrublands, whereas you'll see trees, heavier fuels, shade, moisture, so trees and shrubs as opposed to shrubs and grasslands on the northern aspects. And this just kind of paints that picture. So south-facing slope, north-facing slope. So the sun rays strike south-facing slopes or southern aspects more directly than north-facing slopes in the northern hemisphere. And you can see, so this ray, this ray, this ray, all three of those hitting this southern aspect, whereas you only get a couple here on the northern. And not only do you have more here than you do here, but then these ones, it takes longer to get there, and they're not going to hit it at such a great angle that you're going to get all of the energy that you can from the sun. So just trying to paint that picture again in terms of fuels. So east facing, so you get the earliest heating, but you also get the earliest cooling. North facing, you'll get your heaviest fuels here, so more timber than grass. You get your lowest average temperature, your highest RH, your latest curing of fuels, your latest snow melts, your lowest rate of spread on north-facing slopes or northern aspects. Southern aspects, you get your lightest fuels, your more grass than timber, your highest average temperatures, your lowest average RHs, your earliest curing of fuels, your earliest snow melts, your highest rate of spread. West facing, you get a mixture of fuels, you get latest healing and the latest cooling. So then let's talk about moisture and its effect, because it plays into the idea of temperature. So moisture happens most in the world just towards the equator and decreasing as you go towards the poles. And then if we're thinking about, well, just what about land, like in California? Well, we're going to get the most moisture on the coast and then least amount of moisture as we go inland. In terms of relative humidity, because that's something we talk about a lot in wildland fire ecology. So what is relative humidity? It's the simplest explanation that I like is how much water vapor is in the air versus how much water vapor could be in the air. And so for an example, a relative humidity of 50% means the air is holding 1/2 of the water vapor that it could hold. Now this all depends on temperature, but the idea is that you get this percentage, and the percentage basically lets you know how much water vapor is in the air. So if you have a day where a day or a time, really, because it changes throughout the day, a time where you've got 90% relative humidity. Well, if the air is holding 90% of the water vapor that it could, that means it's probably pretty wet outside. The air's got a lot of moisture in it. Whereas if you go somewhere and there's 10% relative humidity, it's going to be pretty dry. There's not going to be a lot of moisture in the air. You would expect fuels and things to be warm and really dry. And so RH, or relative humidity, really responds to diurnal patterns. And so when you have lower RH, your small fuels, your fine dead fuels, your 1 hour fuels are going to dry out real quickly to the point of ignition. Active burning will be happening during the warmest, driest part of the day. And so when we say the warmest, driest part of the day, those two adjectives, warmest and driest, they go hand in hand because there's an inverse relationship between temperature and moisture. So as the temperature of the day increases, the moisture of the day decreases. And so it's really kind of important to understand that inverse relationship, because when we think about active burning, so when burning is going to be the worst, it's going to be the worst during the warmest, driest part of the day, because the fuels are going to be preheated and ready to go, and the temperature, we're going to have the heat there, so we'll have that oxygen, we'll have the heat, and then the fuels are ready to burn. So that's all the conditions that fire needs to get going. So if there is more moisture, that's going to make it harder. And so if we really just understand this idea of relative humidity and its inverse relationship to temperature, we really understand, okay, it totally makes sense. Active burning happens during the warmest, driest part of the day. Why wouldn't it? It totally makes sense. Another part of moisture in the atmosphere is precipitation, which really affects fine dead fuel moisture. Just dead fuel moisture. It's all of our time-lag classes, right? The 1 hours, the 10 hours, the 100 hours, the 1,000 hours. Now, what's interesting about precipitation is it really depends on the content, the rate, the location, and the type. Well, what do you mean by that? Well, rain versus snow, right? Snow is a different type of moisture. It's going to stay on the fuel bed. It's going to extend the moisture time. So in terms of the type, it's let's say it's snow. The moisture content of snow. Well, snow is it's going to be cold and it's going to stick there and it's going to stay there. The location, where is it going to be? It's going to be at higher elevation. So it's going to stay colder. It's going to be able to stay on the ground. In terms of its rate, it's not really going anywhere until summer comes and the temperature gets high enough to burn it off. So it's much different. It's also different if you think about, the rain during a thunderstorm versus a rain during the frontal event. So if we get rain happening for, 1 hour or 30 minutes. It's much different than rain happening for 6 days in a row. So that's what I mean by it really depends on the content, the rate, the location, and the type, because it's precipitation really it can have a great effect, but it can have a great effect with time and with amount. It can vary greatly. But what's typical though is that moist environments typically have smaller daily temperature ranges than dry ones. And so what that means is places where it rains a lot or places where you got a lot of humidity in the air, you're going to have less of a shift in your daytime temperature ranges as opposed to places where you have dry environments. So here in the Central Valley, we have a pretty dry environment. So we're going to see big time temperature shifts. 30, 40 degrees are not uncommon to see, right? And, you have a day where it's a high of 103 and a low of, 65 or 70. That's not uncommon to see here. It's like, well, if you really do the math, oh yeah, that's like a 33 degree difference or a 35 degree difference. That's a pretty big shift in temperatures. So just looking at this diurnal temperature change and really just focusing on this idea of this inverse relationship, right? Inverse relationship. One goes up, the other goes down. So with temperature during night and during the early morning, relative humidity is highest and our temperature is lowest. And then as the sun starts appearing, starts giving us more solar radiation, temperature goes up. And as temperature goes up, relative humidity goes down. We will see during some part of the day where we could get our maximum fire intensity. Really depends on where we are specifically. For this graph, for this area, it was between 12 o'clock and 1 o'clock in the afternoon. Probably here in California, we'd see it a little bit later throughout the day. And then if we just look at on the right here, same idea, temperature and relative humidity. So during the night, relative humidity is up, temperature is down. Then as the sun starts coming up, starts getting towards its best angle for solar radiation, the temperature goes up, relative humidity goes down. And that's when we say diurnal, if that word is throwing you off because you haven't heard it before, all we're talking about is changes during the day. That's all it means. So why does this change happen? Well, it comes down to the idea of water, because this planet is covered in water. So water has a high specific heat, right? And so we know about the water cycle, so we know about the idea of the evaporation, and we talked about the idea of pressure, and pressure coming from all the little air molecules. So in terms of atmospheric moisture, so because water has a high specific heat, atmospheric moisture absorbs heat during the day and then sheds it at night. So in terms of our moisture, because we get that solar radiation, we're doing evaporation, more, plants are transpiring more, so that moisture is going into the atmosphere and we're heating up, right? Where the ground is getting heated up, so we get more evaporation. But then that heat disappears again. So that means now we don't have to get that evaporation. We don't have to get that moisture loss, and it can and instead we're shedding heat during the night, which means we keep the moisture. Did I forget? I forgot to mention something. Dry air will have higher daytime and cooler nighttime temps than moist ones, and that goes back to what we said earlier about the dry versus the moist environment. So there's a much bigger shift in temperature in dry environments than there is in moist ones. So with this graphic right here, it says wildfire starts versus time of the day. Now, I don't know why they didn't just put midnight here and noon here like they do for all the other ones. They wanted to be different, I guess. But the idea is, so this is the beginning of the afternoon, and you can see beginning of the afternoon into late afternoon and almost into nighttime. That's actually where we get a lot of our wildfire starts. And if you say, well, that seems weird, it's really just the idea of thinking about the fire triangle: fuel, heat, and oxygen. When are we going to have our best mixture of that? Well, oxygen, any time of day. We always have the right amount of oxygen. So then it comes down to heat and fuel. Okay, so when's the hottest part of the day? Well, the hottest part of the day is usually going to be in the afternoon, and usually in the late afternoon. Most days, lately, I think it's been around like 3:30, 4 o'clock sometimes, right? And so if I start looking like 3:30, 4 o'clock, well, that's the beginning of this peak right here. So then what about the idea of fuel? Well, when is fuel going to be the driest? Is it going to be the driest when it's closest to the wettest part of the day, or closest to the driest and warmest part of the day? It's going to be that driest, warmest part of the day. So that makes sense. If the driest, warmest part of the day is somewhere right here, then our wildfire starts are going to go up after we hit that, and then obviously go back down. Now, if you say, well, there's a lot of late starts here, it depends. This is just this is not for everywhere, right? This can vary by the fuel types. It can vary by the location. It can vary by the amount of precipitation you get. But it's just an interesting idea to understand that kind of going with this idea of the effect of weather, that we just, if we kind of add together the basics of what we know about fire plus adding in the idea of weather, we really can start thinking about the fact that when you look at a chart like this, whether it's right or not for this specific area, you can sit there and go, yeah, well, that makes sense. And it makes sense because we know that this is going to be the warmest, driest part of the day, which means that since we already know oxygen's good, then yeah, that's the best time for fire to start. So now let's talk about something that people might not be as familiar with, because I think the ideas of temperature and moisture, people got kind of an idea of that. But let's talk about atmospheric stability.